Good day everyone, I'm Maxine Veloria and today I'm going to tackle about the chapter 18, which is the entropy and the second law of thermodynamics. So what is entropy? So entropy is a measure of the disorder or randomness in a system. So the second law of thermodynamics states that the total entropy of an isolated system will always increase over time. In simpler terms, systems tends to move towards a state of greater disorder. Let's have our first example, which is the ice cube melting. So consider an ice cube in a room. The molecules in the ice are in a relatively ordered crystalline structure. As the ice melts, the molecules gain more freedom to move around in a less structured way, increasing the overall entropy of the system. Next is decaying matter. So decay of organic matter is another example. A dead organism undergoes decay and decomposition, leading to the breakdown of complex structures into simpler molecules. This process results in a higher entropy state. Let's proceed on how to recalculate the change in entropy for a finite process. We must recognize that T is generally not constant if dq sub r is the energy transferred reversibly by heat when the system is at temperature T. The change in entropy is an arbitrary process between an initial state and a final state is the formula presented in my presentation. This equation is the integral form of the second law of thermodynamics, specifically in terms of entropy, Ts, heat transfer dq, and temperature T. ds, this represents a small change in entropy. Entropy is a measure of the system's disorder. dq, this stands for a small amount of heat transferred into or out of the system. Heat is a form of energy transfer. And the T, this represents the temperature of the system in absolute terms, like the Kelvin. We have our example here again. Think of entropy like a backpack you carry around. The weight of the backpack, or the entropy, only depends on how much stuff is in it when you start your day and how much is in it when you finish. It doesn't matter what route you take during the day. The change in weight is the same. Next, inside the backpack, you have a bunch of little things, or the microstates. The more ways these things can be arranged, the more disorder there is. The total disorder is measured by the number of possible arrangements, or the microstates, and this doesn't change as you go about your day. Now, imagine a day where you don't exchange snacks with your friends, so there's no energy transfer as heat. So in this case, the weight of your backpack or the entropy doesn't change. So this type of day is like a superhero day. It's so smooth and efficient that it's called isentropic process. Now let's talk about a special kind of day, a Carnot day. It's like having a super efficient engine that works between two temperatures. On this day, your backpack doesn't get heavier or lighter, so the change in entropy is 0. It's the best day for your backpack or the entropy wise because you're using your snacks or the energy in the most efficient way possible. And if your system goes through a cycle and can undo every step it took, then the overall change in entropy is 0. It's a bit like a magical journey where no matter how much you wander, your total passport stamp collection stays the same when you come back home. Then we can say that integration is over a closed path. Thank you so much for listening.